Hey, Physics 30s. Okay, so we are going to do the photoelectric effect practice questions here. Here's just a refresher question. What's the energy in EV electron volts of a 400 nanometer photon? So we can just quickly do that. Make sure I'm in the right pen mode here. So that would be HC over lambda. I'm not going to do too much here. I'm just going to mention that I'm going to use the 4.14 number here. Seems like the most common one to use because we are communicating our answers. Okay. We're not really using this for any additional math. You'll see might be later on that we will be using the other one when we talk about Compton's effect, the momentum of a photon, et cetera, et cetera. All right. So I'm just going to punch that in my calculator here. Okay, so we get about 3.11 electrovolts. So that 5 rounds up. Pretty good. What's the threshold frequency for cadmium? So this is the frequency in which the wave or the photons would have to be able to eject an electron, have enough energy to eject an electron. Remember, it's a one-to-one thing, so I can't have two photons kind of build up and eject one electron. It's one electron for one photon. That's it. No more, no less. All right? So if I know the work function, which is W in this part of the formula, it's not the same W as work as being energy. It is kind of an energy, but it's not the same as the change of energy. I can use the work function formula. It's very similar to the E formula from the previous one here. I'm just going to rearrange that for work here. So 4.07 electron volts. I'm going to be using the 4.41 times 10 to the negative 15 number. Again, it's going to give me a pretty high frequency. Well, all visible light spectrums are high frequency, but that's not really what we're talking about here. So I get 9.83 times 10 to the 14 hertz. There we go. Will a 500 nanometer photon cause photoemission from cesium? Explain why not. So let's just double check. So this is the work function of cesium. So this is the energy required. This is required to cause photoemission, right? If you have any less than that, nothing happens. So you want to look at the energy of the photon, and we do a little comparison. So I'm going to go HC over lambda. I'm going to be using the 4.14 number. So I'm going to get rid of the lambda here. I'm just going to put in the 500 nanometers right here. Show that that's what I'm using here to calculate this. So 4.14 times 10 to the negative 15 times the speed of light divided by 500 nanometers in meters. I'm going to change it to meters. So I get 2.484 electron volts. Okay. So that's the energy within the photon. You notice that this energy over here, 2.1, is less than that. So that means there is going to be enough energy for this to work, and some of that energy is going to be left over as kinetic energy for the electron that's emitted. So photon has enough energy to, I don't know how you would word that. I'm going to say overcome, maybe? Overcome the work function. That's a good. Cool. What's the stopping voltage you required to stop an electron? A very specific amount of energy. Okay, so I'm just going back to my formula sheet here, pull up the stopping voltage formula, which is, I think I explained in the video, or lesson video, that essentially just the same as one of the other formulas just above it there. What I have here, I get EK max is equal to QV stop. Okay, so I'm going to rearrange this for V stop. EK over. Okay, so this is where it's going to get to use this formula. This EK has to be in joules for this to work. But the fun thing about this is if I change this to joules, which I'm going to do, I might as well just do it. This energy times 1.6 times 10 to the negative 19 joules per EV. So I'm timesing it by 1.6 times 10 to the negative 19. Okay. Then I'm going to divide by 1.6 times 10 to the negative 19. And mathematically, this number, oh, sorry, this is just coulombs here. This will just turn into 1.25 electron volts. Right, it's the same number. Oh, not electron volts, sorry. Why did I say electron volts? It's the same number, different units. Right? But it ends up being the same number. Cool. Explain how stopping potential, which is the voltage, is related to the maximum kinetic energy of the photon. Okay. So they are directly proportional to each other. It's directly proportional. If one goes up, the other one has to go up as well. You could just look at that based on this formula here. V stop is equal to EK over Q. If my EK goes up, so does my V stop. Okay. True or false? The greater intensity of light hitting a metal surface, the greater the stopping potential required to stop the photoelectrons. So remember the definition of intensity. Intensity is the number of photons, not the energy of the photons. So therefore, the photo emissions, the photoelectrons, what's called photo emissions, will not have greater energy there will be more of them with the same energy as before. Hopefully that kind of wording there makes it a little bit easier to understand what's happening. You're just having more and more photons. Each of those photons, it's a 1-for-1 ratio, so they're not going to group together and make one electron more energetic. It's going to be 1-for-1. But if I have more of them, all with the same amount of energy, because it doesn't say that the light has changed its wavelength or anything, same amount of energy, all the electrons that are emitted will also have the same amount of energy they had before. So they wouldn't require any more stopping voltage. Right? So, yeah, so they wouldn't require any more stopping voltage. I'm not going to bother writing that down. There you go. Hopefully you did well with that worksheet, and I'll see you in the next one.